All right, hello world. This is CS50 Live. My name is Colton Ogden, joined today again by CS50's Nick Wong.
Hello.
Nick, what are we talking about today?
So today we're continuing a little bit of our subject from last stream. We're taking a step back for like a moment from images, and then we're hopping into neural networks.
To kind
of the biggest buzzword of ML at the moment. Maybe.
Going a little bit lower level than images, work on slightly simpler data sets.
Yeah, we're going to use a little bit easier data set. When I built kind of a sample version of this last weekend, it took, I think, like an hour to run on an image or so. Not great. So we're going to use a very simple data set and figure out how to just what a neural network is. You know, what is a neuron? Because they're not quite the same as the ones in our heads or in the rest of our bodies. And it's kind of complex. There's a lot of weird terms like backprop and gradient descent and things like that.
None of these things I know, by the way.
Yeah. I didn't know them for quite some time.
We were talking about this before the stream, and there's a lot of jargon, but it'd be cool to
Tons of jargon.
Elucidate what it all means. And if anybody's unfamiliar, CS50 Live is a show hosted here at Harvard University. CS50 is Harvard's Intro to Computer Science, taught by David Malin, who may make an appearance in the chat.
Yeah,
if we are lucky enough.
In there from time to time.
And this is kind of an offshoot of that, where we build things from scratch. We talk about concepts. Nick is a regular here on the stream. We've done not only programming things, but also operating system related things. Kali Linux was a cool thing we talked about.
Might return to that at some point. You know.
And your first thing was actually machine learning related. It was building a classifier.
So that's a very high level approach. We were like, we're going to use some APIs. We're going to just kind of skim over a lot of the math. Now we're going to dive a little bit more into the math. And then we're going to actually end up motivating the high level approach again. But this time we're going to explain each of the kind of lower level concepts that we talked about. Actually, I think in that stream.
That first stream was we used TensorFlow,
which
is Google's
Keras,
library,
which is even higher.
Yeah, Keras. Today we're going to be using
just NumPy.
Just NumPy, yeah. And then that's basically it.
That's it. We got matrices.
With the goal, though, eventually of continue, because this is kind of like a new sub-series.
Yeah, exactly.
Where we're doing sort of like building a neural network, talking about machine learning.
Yep.
With the eventual goal of being able to generate images from prior streams, which we talked about last week.
Yep, and we're going towards that. I think that is our next week. That's where we're going to start hitting you with these like generative neural networks. This kind of like, do we have variational autoencoding? We have kind of like distributional networks, and then we have GANs, which are the generative adversarial networks. And those are like state of the art at the moment. They're super cool.
Those are the things that like generate the really cool landscapes, stuff like that.
They produce all these like very sharp images. So even like kind of like deepfakes is kind of a similar concept where it's like you can't necessarily tell that it's not a real person.
Oh, like the presidential videos where they're like lip
it's a
syncing
little
onto
freaky,
someone else.
It's a little wacky. The other thing that I think we'll probably explore, we might even start with next week because it's a little easier to build from scratch, is style transfer networks. So let's say I give you like a Van Gogh painting and I then hand you a modern day picture of something, and I can transfer that style onto that, and it's beautiful. I mean, they create these just like incredible works of art. And it's pretty easy to build once we have kind of like our basic understanding of like what's a CNN, what is convolution.
There's a lot of steps along the way.
Yeah.
It's kind of overwhelming, but I think it's cool.
It is a lot. So if you're ever confused, luckily it's on video, so you can just kind of pause, go back.
True that. If anybody wants to watch on YouTube, our first part where we built the k-means classifier.
Yes.
Because we're going to eventually need to classify images, so we're presuming to be able to generate them by comparing them against those clusters.
Yeah, exactly.
But yeah, you can check that out. That's on YouTube. That should be a VOD at the time of this recording, actually. True Kane says, hi, Al. Nice job on the podcast, Colton. Thank you very much.
Yeah, nice job.
We are releasing a podcast very soon, probably today. We just filmed it. It's on YouTube, and all the major sort of Spotify, or not all the major Spotify, all the major podcast distribution channels, including Spotify. But that's to be formally announced probably on Facebook and otherwise. But yeah, definitely check that out.
Sweet.
Why Sarah says nice music. Thank you very much. Cool. Thanks so much, everybody, for tuning in. I say let's just, we have a lot to cover today.
We do have a crap ton to cover.
Why don't we just,
we're going to just dive in.
Yeah, let's dive right into it. Let me just do the old magical. Now people can actually see what I'm doing now. I'm hitting a key on the thing. We changed our camera lens.
It's a lot wider.
So boom, there we go. Back to the old C matrix.
My favorite classic C matrix screensaver. Cool. So we're going to hop out of that. And we have an empty file to start.
Programming with brass knuckles.
Yeah,
kind of. Yeah, it kind of looks like that, doesn't it?
I guess, no one had really seen those before, right? Like,
that's true. Yeah. Well, I guess I kind of do this, but it's a little harder to see normally.
Yeah. Oh, that's wild. So we're starting out with a just kind of a raw Python file.
Literally nothing.
Literally
zero.
In order to kind of like keep ourselves on track, I do have a like reference file in case I kind of forget some of the math off the top of my head.
A lot of the stuff is very, there's a lot of details.
Heavy.
A lot of details and
Yeah,
stuff.
and a lot of like very, very down in the nitty gritty details. So we're gonna start with kind of like my favorite import numpy God dang it. That's
As numpy.
as
Nice.
nailed that.
Really
Thank
solving
you,
problems.
IDE. My IDE is like, oh, you want to? We'll abbreviate that for you. We got this. Overeager IDE.
Yeah,
We're going to start with NumPy, and for those that aren't familiar, NumPy is a pretty awesome library. It lets you do all sorts of beautiful things mathematically. It also has just kind of like inbuilt matrix operations and matrices that make all sorts of math really convenient. We're going to have kind of a simple X data set, which is going to be a NumPy array of literally just, we'll put 0, 0, 0, 1. And for those that are kind of curious as to what we're doing right now and why we're doing it, it's a great curiosity to have. Essentially, we're just creating kind of like a toy data set. And the reason that it's really just kind of like a toy thing is the function that we are kind of testing is deterministic. I can, given an input, tell you immediately what the output is. It's human computable. It's not particularly interesting. But it motivates using a neural net because its function is nonlinear and it's not separable in any way by a linear function. Now, if you're familiar with like basis functions, you can actually transform this into a basis in which it is linear. But we're going to pretend like you can't do that in order to force us to use a neural net.
I already don't know some of the things that you're saying. So,
So in case, maybe if you're watching very closely, you'll notice that this is the exclusive OR function. So given exclusively 1, 1 as its input, it will return to you 1. Anything else returns 0. So you'll notice that 2 zeros, that's a 0, and 2 ones, that's also a 0. And this can be generalized to be kind of like the parity of an input. So if I give it like 100 zeros and then 1, 1, it'll also return 1. There are variants on exclusive OR and kind of like applications of it that also carry these properties. But we're going to start with the simplest possible data set. You'll notice we're ignoring like batching. We're not going to split this into training and validation and testing. We're not going to do any of that. There's no unlabeled data. This is very much just like a toy set, and we want to figure out how to build a neural net on top of that. And speaking of, neural net is kind of like this term that gets thrown around all the time. It's not necessarily intuitive like what it is. It's a network of some sort, but even that's not super intuitively defined. Network meaning things can talk to each other, and there is some path by which they do that. Now, that path sounds kind of simple in this high-level overview, but as we go into it, you'll notice that there's a lot of math involved. And then the neural part is where we'll start, which is, what's a neuron? And it's modeled after the idea of, our heads. In our heads, we have this these like billions of neurons that all communicate with each other, and they do something that was for a long time thought to be very simple. You gave them some sort of stimulus and they either fired an action potential or didn't. That's the biological neurons. Now, that's not quite true. There's kind of a hidden complexity to neurons where they actually have kind of like dendrites that poke out, and those can also fire mini potentials, and then certain accumulations of these potentials can then fire the overall neuron's action potential. And what that means and why it's interesting is now we have a way to do nonlinear action potentials. We can do all sorts of wild things in our heads. It partially also explains why our brains are so complex, or at least gives an understanding for the intuition why. Now, the neurons that we're building are a lot simpler. They're modeled in the same concept, but it's not quite analogous. So the neural, sorry, Blue Booger just posted in our chat, said, my brain is a neural network. It only contains zeros, no ones.
That's great.
I'm sure that's not true, but a very funny joke. So our neural network and neural networks in general, they consist of, each neuron is essentially one weight and one bias. Now, to say it that way sounds a little funny, and if you're familiar with this at all, hearing that is a little whack, but that's kind of the intuition is I have some weight, which is just a number that says, hey, anytime I'm given an input, I'm going to apply this number to that input, and I have some bias. So I know somehow that I am off linearly from whatever the actual answer is. If you're familiar with like y equals mx plus b, that would be like the b term, and then m might be your weight. Now, that's not quite how this works. It's all done through matrix math, so things get generalized a little bit more broadly, but that's kind of the intuition, is every time a piece of, or an input feature is given, the neuron that gets it says, I'm going to multiply you by a weight, add a bias, and I'm going to pass you on to the next layer. We're going to build a single layer neural network, which some of you may go, that's silly. And it is, to a degree. A couple, maybe like 40 years ago, not so silly, but now it is kind of silly. We have GPUs, we can calculate like hundreds of neurons in one layer at a time and things like that. And this will not restrict us as far as number of neurons we have, but it will restrict us in number of layers we have. And the reason for that is there are a couple algorithms that I want to very much like explain very clearly. But if we were to generalize this to a general network with many layers, that might be, some of that clarity might be lost in just the syntax of the code. So I'm going to try and avoid doing that. So yeah, what we're going to do is we're going to just, if I could spell. If you all have seen the streams before, I can't spell for the life of me. At least not when I'm coding.
It's the curse, though.
It's always the curse of live stream coding. I'm going to get rid of this window, actually. So we have some neuron. I'm going to call it neurons, actually. And that's just the number of neurons in our hidden layer. We have our like input dimension, which is our x.shape.
And what is a hidden layer?
So oh, right, that's a great point. So in these networks, I forgot to explain the network part of network. The things that are communicating with each other are these different layers. And so if we imagine a network, I like to imagine it as like I'm standing on top of it looking down, or I'm standing at the bottom looking up. I don't know why that's the way I imagine it.
Usually I see it as like a left to right. Like you see
yeah,
the layers,
also
like the vertical layers.
Yeah, you know what? Let's do that. Let's imagine it from like left to right.
You want to maybe pull up like a picture on Google or something?
Yeah,
like
let's illustrate this a little bit.
Very nice changing background, by the way.
Thank you, thank you. I'm a huge fan of just pretty pictures. It helps me remember that the world is normal outside school. Nothing against school. So a lot of people, I think, imagine it like this. And this is a good image for what we're doing because instead of having two hidden layers, we just have one.
I see. So a hidden layer is not anything that's not the input or output.
Exactly. So from the outside observer, you can think of it as like the black box part. I just have to configure my thing to work with your input layer.
Input would be like your eyes,
get an output.
kind of.
Exactly.
And then I guess a hidden layer would be your brain completely.
Yeah, it's kind of like most of your brain, and then what you think of is the output layer.
Right.
So it's kind of like as it goes through, you eventually then figure out something, and you're like, oh, and that's your output.
Layers like Shrek.
Yeah.
Yes.
Layers like Shrek, except in this, well, yeah, we'll say that that's roughly true. These are often referred to as dense layers because, and there is kind of a cool Facebook comment somewhere by I think a software engineer, probably an ML engineer, who said that like there is no such thing as a truly like a full. True fully connected layer. These are often referred to as fully connected layers. Their point is that like in order to do that would be almost impossible. And you know, you can go Google that if you'd like. But essentially these are referred to as like your dense just neuron layers. There's nothing super crazy about them. They basically are just these like weights that can be applied, biases that can be applied, and they all talk to one another. So every neuron from one layer influences the neurons from the next. You can change that concept in order to get different behaviors. There's all sorts of things. This is just kind of like the very simple, like, what exactly are we talking about? Excuse me. So in this image, you have each circle represents one neuron. In the input layer, each circle does not represent a neuron. Instead, each circle represents one in particular aspect or feature of the input. And then the circle of the output layer represents our like prediction. Given some input, what class do we think it's in? So going back to I'm going to organize that a little bit better so I can switch quickly between them. Going back to this, we have our input dimensions. We have our output dimensions, which is equal to our y.shape. And from there, all we're trying to do is figure out how to set up a hidden layer of some sort. Now, initializing the weights for any sort of like input dimension, output dimension, hidden layer, prediction layer, generally there's all sorts of like initializations that you can use with those. We're going to use just NumPy's random uniform to do that. So what I'm going to do is I'm going to initialize my hidden weights. Is going to actually be equal to numpy.random. I can never spell. I almost typed random.weights.uniform. Spelling is just, it's killing me today. And then I believe it's size, yeah, size equals. So when we have this like hidden layers weights, we know we're going to multiply them by whatever the input is. And our input's shape, you'll notice, is like an n by 2. So we'll probably transpose that in order to get it to work properly. But let's imagine that we're actually doing the input layer or our hidden layer, which is what we're going to kind of throw things into, as some sort of number of neurons. So this is just neurons by whatever the shape of our input is. So this is input dimensions 1, and there are better ways of generalizing this, but I don't want to spend too much time on like matrix math and drawing these out. I also don't have the ability to draw, so in general, I also can't draw for the life of me. So we're going to just pretend that this is how this is going to work. And then we want our output weights as well. And this is, again, going to be just a random uniform, random dot uniform with a size. And again, we want to kind of like consider the matrix math of this. It's a little bit tricky if you're not super familiar with how matrices work. There's all sorts of great tutorials online. Khan Academy has some awesome like linear algebra tutorials. I would recommend going through them. A lot of machine learning is basically just linear algebra, at least at the like mathematical level. But to say that it is only linear algebra or only statistics misses out on the kind of emergent behavior and other properties that arise while you're performing machine learning. So what we're going to do here is, because we're now multiplying by whatever our input layer, our hidden layer handed to us in order to output something, is we're going to say, okay, whatever our output dimension should be, and again 1 by the neurons. And so now whatever we kind of throw through this, we should be able to figure out the dimensions, and everything should roughly translate correctly. For just kind of our own benefit, I'm going to print these out. They're not particularly wild. Oops, I don't know why I pressed tab. But we'll see why they work. Here you go. So we printed out the hidden weights, which is this part of our code, and then the other half is the output weights. And essentially what we're looking at is we have something that is roughly 4 by 2, and then we have something that is 1 layer by 4. So that should make sense. We have 4 neurons. If I were to change this to 8 neurons, you'll see this grow. And again, we have this 8 by 2, which makes sense. Our input shape second half is going to be just 2. And then our output shape has this 1 by 8. And that should also make sense to us. Cool. So once we have all of these things kind of set up, we also need to initialize our biases. And biases, you don't start out biased, kind of in a weird metaphysical, philosophical sense. You aren't born biased, at least not, well, supposedly. And so we're going to also initialize our biases to just zeros. And the thing with bias is that essentially you're adding bias to the product of the weights and whatever they're being multiplied with. So if we think about this kind of matrix style, our hidden weights have this shape of, of whatever our neurons number is by the input dimension. So once you multiply that by the input dimension, we then have some resulting shape. If you're familiar with a whole lot of matrix math, then if I take something that is, we'll say, 4 by 2, and I multiply that by something that is 2 by n, then each kind of stack, I don't know why I'm kind of illustrating it like this, but I think that this is a very convenient way to imagine how this will work. Each element of the input is then going to go down that matrix and be summed up into the corresponding column and row pair. If what I just said didn't make any sense, let me find an example to illustrate that. It's a little tricky to see. I would like an example. Oh, here you go. So I'm a very visual person. This is not necessarily the biggest image I could have found, but that might help. Essentially, you're going to take a column from the thing being multiplied and multiply each corresponding entry by the row of the thing multiplying, and then you're going to sum all of those up and put them in the corresponding like ith row, jth column, and you'll do that each time. And so you might intuit that something that's I was going to say n by m, but that's really difficult to hear the difference, so I'll say n by p. So let's say this is n rows, p columns. If I multiply that by something that is p rows, you'll notice that p and p have to be the same in order for this to work. P rows by q columns, then I'll end up with something that's n by q. And that hopefully makes sense. If not, Yeah, as Tuxman and I have mentioned, go to Khan Academy, maybe practice a little bit with your matrix math, things like that.
So this would be 7 plus 18 plus 33?
Yes, very nice. Yeah, and so what Colton just did there is he said, okay, 7 times 1, 9 times 2, 11 times 3, and so on. We're going to kind of like fiddle around with how these work. It's not, even I struggle to like keep track of them in my head at all times. It's not super intuitive. It's not the way humans really think, so don't worry about it if it's something that bothers you. But you should always be able to like write it out and kind of like imagine how these work. I'm positive you will see me mess these up pretty much at least 3 times on this stream, maybe more. You know, like we'll play golf with this.
That's what makes it fun.
Yeah, it'll be kind of entertaining. I'm sure some of you will be like, wait, no, transpose that. That's another thing is we'll use a lot of matrix terminology, like a dot product, multiplication, matrix exponentiation, and transpose. And I think that the first 2 are the really key ones, like dot product and and transpose. So if we were to transpose this matrix, then you can imagine you like flip it across its diagonal. So it would, instead of being this like 2 by 3 matrix, it would now be 3 by 2, and you would just kind of rotate it around. Now you will notice that if you transpose this first matrix, it is no longer possible to compute this multiplication, this dot product, because the rows and columns do not match up, so things won't work anymore.
Right. Yeah.
Symmetric matrices always retain their, square matrices always retain their dimensionality because they're n by n. So if I transpose it, it's still n by n, but they don't necessarily retain their properties because they're flipped. But if it's a symmetric n square matrix, then transpose is equivalent to itself. So transposition is the identity function for a symmetric square matrix.
What is the best book to learn JavaScript?
I
don't think I haven't
Google?
seen a recent book or I haven't read a recent book in JavaScript, but there's like a ton of. I feel like anybody now can just go on YouTube and probably find like an 8-hour video on like the basics of JavaScript, probably.
Yeah, I agree with that.
Especially, I'd recommend probably looking into newer versions of JavaScript, like ES6, ES 2015 JavaScript. Because that's kind of becoming the norm. Also, apologies, I had to tune out because our Facebook stream did not go live. So I was kind of like typing and figuring stuff out off to the side for a few minutes. So I missed a lot of what you were explaining.
No, it's all good. And I'm sure we'll have to explain it a couple of times actually in this stream. So what we're doing right now is we're saying, okay, we have these kind of, our neural architecture, our layers have these weights and these biases, and we need to initialize them. So we basically need to initialize all of our neurons. The hidden layer, and actually just in general, I've initialized them all to these uniform weights. So we'll actually print, or we've been printing out what those kind of look like. They're just uniformly distributed numbers from 0 to 1. And essentially generally speaking, there are many ways to initialize this. I could use like I think there's or I could use a gamma function here, but I could also use like I think it's normal. Yeah, I could use a normal function and do this. There are many different ways to do it. Uniform is just a very kind of like vanilla. If you don't really know how your input's going to behave, this is a pretty decent place to start.
Just like a normal distribution random number, basically?
So this is just a uniform distribution,
Okay.
but you could use a normal distribution if you like,
Gotcha.
and give it some other parameters. Like if we wanted this to be a normal distributed one, I believe I have to give it a location and scale. Oh no, they initialize to a standard normal. So I could equivalently normalize or put these as normal distributions, and then if I print them out, and actually might be also informative is for me to print this.
I'm so proud that you're using format strings.
Thank you. I learned from this. Oh, not that. Weights, although it actually wouldn't matter. And then if we, and then if we do standard deviation on the same thing, np.std. It's really confusing. NumPy and R use different abbreviations for standard deviation, and it's always very, very confusing. So you'll notice on like a pretty small data set, our mean is actually non-trivially distant from 0, but our standard deviation is again non-trivially distant from 1, but it's like pretty close. So essentially, the larger these become, so if we were to use like 1,600 of these neurons, I'm going to not print those weights anymore, that'd be huge. You'll notice that our mean is now very close to 0, our standard deviation is now very close to 1. If you've taken a stats class, there are ways of measuring what very close means, but essentially, this should have a normal distribution, is what we're saying. But if we switch this back to a uniform distribution, which I'm going to start with, but we can see how swapping these out might change things, although in this example it might not be super easy. The expected value of a uniform distribution from 0 to 1 should be about 0.5, and we see that here. The standard deviation I don't know off the top of my head, but It's around 0.33. Sounds reasonable to me.
So what are these weights eventually going to be used for?
Right. So these weights are our model. So if you are trying to say like, oh, I'm saving my model or I want to use it later to make a prediction, this is what we're using. Is essentially I have some set of weights, some set of biases, and I want to know how do these, how does my model think the input that it's given these weights and biases, should be classified. And essentially what it does is it's going to multiply these weights by whatever the input is. It's going to pass them through the layers. And then once we get to the end, it's going to say, based on what I know and what I'm currently set at, I'm going to spit out a number.
Okay.
So what we're going to do is we're going to
looking
get
for
into that. So what we would end up wanting is some format of this. We want either 0 or 1, so it's a binary classifier in this case, but more generally speaking, if we give it a set of classes, we want it to spit out something that's close to one of those classes, and we'll pretend as if it is. What it actually ends up spitting out is a probability that it's either of those classes, and in this case, it actually spits out something a little strange, but we'll kind of see how that looks in a moment.
And these biases, how do these operate? What's the relevance of the biases? Just
So
trying to
bias is
understand all the
basically
bits and
like a way
pieces.
to correct based on like, I'm totally right, but I'm just like off every time. Like every time I answer, I got like the pattern right, but I'm off by a little bit. And so I'm just going to say, okay, we're going to add in this bias term that says you're biased, and we're going to just correct back towards whatever you should have been because you got the pattern right. You're just consistently shifted by 1. Or by some number. And so that's what that bias does, is it kind of just corrects you back towards wherever you should have been. This is not to be confused with a regularizer, which says every time your model gets like too complex, we punish you more. And we won't actually use a regularizer, not really in this case, but if you've looked at any sort of kind of like introduction to ML, usually people start with like linear regression and then they hop into the ridge regression, and ridge regression is literally just like a regularized version of linear regression. So I say, hey, my model gets too complex, you should have a higher loss for that. Loss is another key term we should define. Loss is a way of measuring how poorly our model is doing. The higher the loss, the worse we're doing. Loss in absolute terms, like the number 3 versus the number 5, that's not super meaningful, but in a relative sense, it is super meaningful. So if I have a loss of 5 versus a loss of 3 versus a loss of 0.01, then the latter is the best version of our model given our data. Loss deals a lot with like a lot of the ways that people come up with these loss functions either deal with like a maybe for a linear function, it's root mean squared error. So I take the square root of the mean of the squared errors from some given knowledge that I have on this. And that would be supervised learning. I know the answers of some of the data set, and I can tell you how far off your model is on those answers. There are other forms of loss, like the one we'll use here, which is categorical cross entropy. Wow, that sounds awful when you say it out loud. And that's not nearly as terrible sounding as it, as it's not nearly as terrible as it sounds. It basically just says entropy is a measure of kind of disorder, and in this sense can actually be interpreted as a form of error. And categorical and cross mean that we have a categorical problem, so we have several categories, we're trying to distinguish between them, and then cross means across these categories, what is the entropy, is where that comes in. And so we're essentially saying, given the categories that we have, given all the like classes that we're trying to form, then what is my like set of mistakes, or like how large are my mistakes? And the reason we don't use like a root mean squared error is that we're predicting on something that's nonlinear. So using some sort of non-existent thing will not, trying to fit a linear function to something that is by nature not linear might result in us not having what's called a like convex function. And that's no good. So because we then can't minimize, we can't come to some global minimum. I think Swag the Swag says, I took too much Adderall. Nope, I actually don't even drink coffee. I just have too much energy. I wish I could drink coffee because sometimes I get really tired, but oh well, no coffee for me. When I do drink coffee, I'm wild. Like I'm just going and nothing can stop me. I also just can't sleep. So, you know, it's a wild time. Anyway, I'm gonna just double check myself. I think I'm right, but I would like to just be sure. Cool. And I called these other things in my reference sheet, but that's okay. And yeah, so Sarl CS, thank you. They say in defense, things do involve a lot of, or the neural networks do involve a lot of math in the background of how they work. Can't help it unless you want it to be a complete black box. I thoroughly agree. We're basically trying to avoid the pattern of a lot of tutorials on the internet, which is like, just use TensorFlow or Keras or get away from like the math. we're trying to show that the math is not necessarily super crazy, though it does require like some algebra, some linear algebra, and a little bit of like probability theory. So you do need some of those things, but after that it becomes relatively accessible. So now that we have kind of our hidden weights, let's take a look at what it looks like to multiply things across. So what I'm going to do is I just want to print out what happens if I do like a hidden weights multiplied by our x.t. So we know that x.t is actually now 2 by n, where n is the number of samples. It's 2 by 4 in this case, because 4 is how many samples we have. And now, based on the fact that our hidden weights is, 4, which is the number of neurons, by the input dimension, this should match up, and we should get some reasonable number. Now, this isn't necessarily exactly what we wanted. Yeah, sorry. Whoa, that's a lot. Oh, right. I also put this up here. Forgot about that. We're also going to actually just do np's dot method to kind of clarify what exactly we're using, because we don't want an element-wise multiplication. So this is the actual dot product of the two. Multiplication, when numpy uses it, is actually just like an element-wise multiplication. So that's not what I wanted to do. The dot product is exactly what I wanted to do. So I take my hidden weights and I say, okay, now multiply those by whatever our input is. And once we have that, we can say, okay, well, if we were to do this for just one x input, we should end up with something that's just one of those rows. And that's pretty reasonable. From there, we're going to just use the rest of them. Which
Shout out
is
to David in the chat. Made an appearance.
Hey, David. Yeah, so hopefully, I almost slipped back into like TF mode where I was like, and any questions? And I was going to wait for a response, and it was just nonsensical. Cool, so we can get this dot product. It's not necessarily super meaningful to us, but we do have one. Now from here, what we're trying to do is then add in our bias. So adding in bias in this case isn't really going to tell us a whole lot. It doesn't necessarily offset anything. We don't gain anything from that. Bias is already still 0, so we're like, well, cool, we've added 0 to nothing. So there's nothing interesting there, but we do need to introduce something called like a nonlinearity to what we are doing. And essentially what that does is it helps us kind of in the nonlinearity functions we're using, it helps us distinguish more clearly between two classes, but also in general, the problem we're trying to solve is kind of by definition nonlinear. So the features that we're using, we want to ensure that we understand something about their interaction rather than assuming that their interaction is linear. I believe what I used in my reference is unrectified. Oh no, I used tan. Okay, cool. So what I did was I said, and you can see this here, is I took the tan, or the tan h, sorry, the hyperbolic tan of this result. So what I'm going to do is I'm going to say, okay, tan h. You'll notice that this comes up all the time when we're talking about machine learning stuff, and all of its siblings and cousins come up too. So tan h is amongst a series of functions that are used as what are called activations. What we're going to do is implement those ourselves. So we're going to build tan h. It's not crazy. None of these functions are particularly wild. But we do have to define it. And so tan h is essentially just sine h over cosine h. And if you're familiar with the approximation of those, approximations to those functions, you can actually manipulate them using their non-real valued equivalents, where like I think e to the ix is equivalent to like cosine of x minus or plus I sine of x or something along those lines. And because of that property, we can actually get a numerator for tan h that looks something like e to the, we'll use np.exp of like 2 times x minus 1, and then we'll get a denominator that looks like something like this, 2 times x plus 1, and then we'll return the numerator divided by the denominator. Now, if we want to see what this function looks like, I'm actually going to just comment this out for a second, and I'm going to graph what that function might look like. And I'm going to have to do this several times, so I'm going to actually just define plot fx. And this is given some fx, then what I want to do is our kind of x is equivalent to numpy.linspace.
First, when you said plot effects, I thought you meant like effects.
That is very, very close, but not quite. And then I'll do like a plot.figure, plot. Scatter of x by f of x of x. Oh, that was wild. If that was confusing, don't worry, I confused myself as well. And then I just need plot, so we're going to import matplotlib. Thank you. Oh no, that's so close. There we go. As plot. Okay, so now I can plot any function more or less, as long as I didn't mess anything up. So now I should be able to plot fx of tan h and see what it looks like. So if I run this, nothing happened, and here's what our tan h function looks like.
I've definitely seen this kind of a curve before.
Oh yeah, you'll notice this curve comes up all the time in activations. It's actually really interesting because you might be wondering, why is this curve so useful? And it's because of this property where it roughly approximates what the step function might look like. So let's say for everything less than 0, I'm just at -1, and everything greater than 0, I'm at 1. And there's no intersection in between. That would be kind of a perfect classifier, right? You're either one or the other.
It's kind of like I guess binary logic, like circuitry.
Yeah, exactly. Yeah, it's literally where it comes from. Is like we have this square wave logic. The problem is that that's not quite continuous. I can't differentiate that conveniently. Now you might say, oh, well, the differential of that is x, but it's a little bit difficult to manipulate. So we use this very nice continuous function that I then understand the mathematical properties of. Now there are several of these. Someone in the chat says, it looks sigmoid. You're right. In fact, why don't we plot the sigmoid function just for funsies? We'll need it later anyway. So let's define a sigmoid of x is, I think we can just return like 1 point divided by, I don't know, it's like 1 plus np.exp of -x. I don't know. Correct me if I'm wrong, but I think that's about right. And if we plot that, plot fx of sigmoid, then we can control C out of that. I always forget, pyplot doesn't really like control C'ing. So here's our tan h function, and you'll notice that it looks very similar to our sigmoid function. Now, tan h is a little bit stricter. You'll notice I can't really switch back and forth between the two, but no, sorry. I didn't plot them quite like that. But you'll notice that our tan h function had a very kind of harsh, almost vertical line in the middle, whereas our sigmoid function actually is a little bit softer. It's a little bit more generous, if you will, about how it plots things. So because of that, it ends up being a little bit less convenient since we know we have exactly 2 classes, but you'll see sigmoid activations all the time. These kinds of activation functions are useful because they push things into one or the other, except when it's uncertain, and this uncertainty can kind of be quantified by where you are on this curve. So basically, if you're in an extreme case, you're just one or the other. If you're not in an extreme case, then I can't necessarily tell, and I might give you some probability using something called Softmax on where you are. Now, if that doesn't make any sense, or if all of these sorts of things look crazy, then don't worry, you're welcome to go Google them. They have very similar, or they have the same names kind of all over the place, so don't worry about it. But these are kind of the 2. We're going to use tan h for now, but we'll use other ones for, later on. Now, oh, yep.
I was going to say thanks to Graham Waltzman saying good night, people. See you all tomorrow. Just wanted to say
yeah, have a good night.
Good night. Thanks for tuning in. And some other people asking, I think Bavik asked if it was similar to a Taylor series, I think, where you were talking about earlier.
So Bavik Knight, you're asking, I'm not exactly sure which part you're asking is similar to a Taylor series. For those that aren't familiar, a Taylor series is a way of kind of approximating functions by expanding out their terms. For example, like the Taylor expansion of e to the x is 1 plus x squared or something. And you can essentially just use the first 2 terms and it always works. Not quite. In this case, there is actually a complex relation with e to the x.
For the tan h approximation?
Yeah. So this is Euler's formula. Oh, cool, I got it right. So it's e to the ix equals cosine of x plus I sine of x. And essentially, when you're going into tan h, you can use, I believe, something like that. Haven't quite seen tan h in a long time, or at least the derivation of it.
How is your Wikipedia styled differently?
Oh, yeah, so I have a plugin for an extension. I love extensions. I can customize everything. My extension for Chrome rehashes, or reformats the text over things.
That's fascinating.
Yeah, so there's all sorts of things you can do here. They kind of walk through how hyperbolic sine can be approximated like this, and cosine, and so on, and then you divide one by the other. So I guess my Euler's formula usage was not quite here, although you could presumably also do that way. And I think someone said in the chat that Taylor series is for like polynomial functions. You can use it for polynomial functions. It's often used that way. It also works totally fine as approximations for like sinusoidal functions or like lower order polynomial functions. It works for general functions as well. It becomes less useful in a lot of cases where the behavior changes away from 0. But it is generally, you're absolutely correct that it's generally used for polynomial functions. Like usually if I have like an e to the x or I have like some weird polynomial and I just want to like approximate its behavior, you can do that. You also have like the Maclaurin series, which is like a specific, I always forget if it's a specific case of Taylor or the other way around. But one of them is centered only at 0. I believe Taylor is centered at 0. Maybe Maclaurin is centered at 0. Taylor has other centers. And essentially because of that, you can like approximate the behavior of a function at any input. And then you can generalize that to multidimensional inputs and also higher order functions. So you can use it for like trigonometric functions as well. It's not necessarily as like informative at all times, but it can be. And then as Al Gore said, well, I never thought I would say that in my life, said if you use like a signal processing or a systems class, they use like a Fourier series, which is to approximate periodic functions. And Fourier series and Fourier transforms have all sorts of beautiful properties such that like random noise is really high frequency, and if I do a fast Fourier transform on an input signal of amplitudes, then I can kind of ignore the noise because it's going to be very high frequency, and then at least usually noise is high frequency compared to the actual signal that I'm looking for, and I can use that to clean signals. There's all sorts of cool things you can do with those. There's many different kinds of series that can be used. Fourier series just happens to be very, very commonly used. Signal processing is a very useful course to take. I actually had to take it last semester for bioengineering, so I ended up absorbing lots and lots of information.
Is that not a class that CS undergrads typically take?
No, yeah, it's not required for CS. It's required for BioE though, for all of our engineering concentrators actually.
Cool.
Maybe not all engineering, I think just BioE. So yeah, hopping from there, we now have this kind of like hidden, we'll call it results, if you will. And that's equivalent to just whatever our hidden layer spits back at us. Now from there, what we want to do is then say, okay, well, what is our output results? What do we do with these hidden layers pieces? And I just kind of want to like go clarify which version I used. Okay, I used a sigmoid for that. Cool. So then here, when we want to see what our output, and I'm going to actually just call this a prediction. This is going to be, I'll do it the same way that I did the previous one. We're going to again do a dot product, and again of its weight, our output weights. But this time it's going to be of our hidden results. And then we're going to add in the output bias. And here we can print out what these predictions kind of look like. Calling it prediction is a little misleading because we currently have not set up a full neural network. But you'll notice that this is slightly different from what we had before, but not terribly distinct. And then what we're going to do is apply the sigmoid function to that. And so again, it's a non-linearized activation, and you'll notice that it also eliminates that like 0 term here. Sarl CS says that our stream will go about 2 hours and 15 minutes, going by my streams in general. Pretty much nailed it. That's pretty much exactly what we're going to do. And hopefully we'll get to the end where we're like, and that was a ton of work. So next time we're going to do the same thing we did in like 50 lines of code in like 1 using TensorFlow. But that is kind of the end in sight, if you will. So yeah, we've applied this sigmoid activation function to this. And you might go, OK, that doesn't really look like a great prediction, but sure. And what you'll then want to have the ability to do is say, how do I like get a probability of these? And probabilities should only range from 0 to 1 and so on. So what I'm going to do is called a Softmax function. What this does is it says, OK, let's take e to the x. Oh, that's just not, that's how you math write that. E to the x is our numerator, and our denominator is actually just the sum of all of those. So I'm going to just do the np.sum of np.exp of x. And the reason that this is really useful is that we can then say, OK, this has specific properties. So given that I was given some x, I raise e to that power, so I now know that I can't have a negative probability. So that's one property of probabilities that I'm going to keep. And then the other one is that because I'm dividing by the sum of all of them, now each of my probabilities has to sum to 1. All of my probabilities together now sums to 1. And that is another property of probability. It's the kind of like law of total probability, is that we're going to have all of our things accounted for. I can't have like, well, the probability of a coin landing on one, or we'll say a strictly two-dimensional coin landing on one side is 0.4, and the chance of it having on the other side is 0.4. 0.2% of the time it just disappears. That would be nonsensical. Well, and depending on kind of what kind of coin, maybe not. But we're going to pretend like that would be nonsensical. So now if I apply softmax to and the problem with softmax in this case is that it actually doesn't quite do what we think it does, because it's not built to apply over several different predictions. So we're going to just have it apply to the first prediction, and we'll print out both. And now what we see is we have roughly even distribution of like all of our possible predictions for this. Now, our neural network is set up a little weirdly in that this should only be either 0 or 1, but you'll notice that we have 4 spots. We're going to kind of just ignore that for today. We'll set it up a little bit more formally next time when we're using the actual implementation, but this allows us to kind of get this roughly right. I don't think softmax works on prediction raw, but it might. I'm not entirely sure. Oh, okay. So you'll notice that if we run it on all of the predictions, we're now dividing by the total sum, and that means that the probability of each of them is now relative over several different samples. That's not quite what we wanted to do, so we're not gonna necessarily do that. Also, I think this might actually be the wrong dimensionality. There we go. That's a little bit cleaner. But again, we just want that first kind of pairing. But you'll notice for each of our inputs, we now actually should reshape prediction in order to get this mostly right. So calculating softmax in this way is a little strange. But if we look at our prediction, it should be a little bit more meaningful to us, as we have now reduced it based on, let me see if I can make that a little bit clearer. We've now reduced it based on, I forgot what I was saying. Oh well. We reduced it to only calculating on one input.
The classic brain fart.
Yeah, I was just like, and the words are out. But yeah, now we know what we're trying to say. Now we're all good. And so that is our actual prediction on that. But we're going to keep the sigmoid prediction because that is what we're going to feed into each epoch of this layer. And we call this kind of part of this the forward pass. And so essentially what goes on here is this is where we're going forward through our network. So if we imagine it as Colton kind of brought up from left to right, where our input is on our left and our output's on our right, then the forward pass is just the forward part of that. Now that would be great if we could just run this over and over again, and that would kind of just make everything work. Sorry, I put the forward pass label in the wrong place. But the kind of problem is that a neural network has to adjust itself, and it's modeled on human learning. So if I do something really silly, like maybe stick my hand in a fire or something, then a human is going to say, oh, that hurt. I don't want to do that again, right? There was some set of stimuli that I now have mapped to my head, and I'm going to say, oh, if I see a literal flame, I'm not going to stick my hand to that anymore. Now, you'll notice that this actually analogizes, and the analogy is pretty solid from like humans to machines in this case, where I don't necessarily have a general understanding that I shouldn't touch things that are extremely hot, and I can't always predict what things are very hot. But over time, we learn some features of heated things. They tend to change color, for example, and look white or yellow or red. Now, once I've started to learn those features over time, I might say, hey, that thing looks like it's really hot. Now, we can't look at something and tell its temperature. That's crazy. But we can kind of use proxies for temperature in order to accurately predict the underlying state, maybe the latent state, if you will. And because of that kind of ability of humans, we wanted to mimic that in machines. And so essentially what's going on here is we want to be able to say, okay, how do I give the ouch response to a machine, and then how do I get it to adjust its future behavior based on that response? So those are the next two parts of the kind of neural network ideology. And the first one is kind of that ouch, like that was wrong, you messed up. And the way that we do that is we take our predictions and we say how far off were our predictions from our actual answers. And then we're going to quantify this in the categorical cross-entropic way. I'm going to just kind of copy that formula because I don't want to recall it from memory. I'll try it from memory and then we'll just copy it so it works. And essentially what that's going to tell us is, okay, this is how ouch that was, how much it hurt. It's often referred to as cost. Can also be referred to as like a log probability, a log loss. And those all mean slightly different things. And in our scenario, they happen to be the same because we're defining our log probability and like a slight manipulation of that log probability as our error. So we're going to say, let's see, log probability is equivalent to it's np.multiply of np.log of our prediction. Yeah, this is gonna be good. Y.t, comma, or not comma there, yeah, comma here of something. Yep, sorry, we made it so far. We'll see how close that first part was. I'm gonna just kind of copy that over and paste it, and I'll paste it below so we can see. Yeah, not terrible. So it's not quite this, it's actually just here. And then we can kind of go from there, plus np.multiply of 1 minus our y.t and np.log of 1 minus our prediction.
Thanks to True Kenny's for kindly putting in, I think what your suggestion was last week, the pattern recognition machine learning book.
Oh, sweet, yeah.
Book.
Yeah, the Bishop book is quite good. We use it in our class for 181, or for our ML class, and that's great. It does a really good job. I think it's pretty awesome. Yeah, there are all sorts of like reading and resources out there. You'll notice that a lot of like tutorials kind of skip over the math, or if they go into the math, they go like way into it. We're trying to go like halfway and kind of like talk a little bit about the math, but also skate over some parts of it. If you don't agree with that methodology, sorry, our bad, I guess. And essentially what we're just trying to do here is give you an intuition for how this works and give you some of the math and some of the like names of things so you know what to Google. So essentially this should print out for us the error, nice.
Thanks also to Cellcrowd, who says, longtime YouTube follower, finally registered on Twitch. Love the vids, keep up the good work, guys.
Thank you.
That's awesome. Thanks so much thanks so much for tuning in on Twitch.
And so you'll notice, or I always say you'll notice, and some people do, some people don't.
I probably don't. Most of the things
I don't even know if I do all the time, but you know. Essentially what happened here is I now have printed out this quantified error. I'm going to go into the math of this a little bit so that we understand somewhat where it came from, but I'm not going to, like, it won't be required that you understand all of this math. You're welcome to go and kind of figure it out on your own, but essentially what's going on here is I'm saying, okay, I want to do this multiplication of the log of our prediction by the actual prediction. So the reason that this kind of ends up working is we're trying to quantify how far we were from our prediction, and we don't necessarily want to use a linear version of that. So logs and logarithms and their properties help us kind of take care of this. You'll notice that multiplying like np.log of prediction by y of t is essentially taking prediction to the power of y.t. If you're familiar with your log properties, then we are essentially taking our prediction and putting it to the power of whatever y.t is. And in our scenario, that's not intuitively useful. However, if y of t or y.t was actually indicator variables, or one-hot encoding, if you will, then this would actually be very helpful, because every time you raise it to the wrong place, it's not going to, it'll have 0, it won't count for our error. But if you raise it, or sorry, every time you raise it to the right place, it won't count for our error. But if you raise it to the wrong place, it will. And that's essentially what we're looking for here.
True Kenny is asking, do I understand this? The honest answer is not that well. I'm looking up some stuff on the side, like the Softmax function, just to better understand
it's Softmax pulled up.
Just to kind of see if I can pull along, but I know that if I keep asking too many questions, we'll be here all day. So.
No, you're welcome. Ask away. We're getting there, and it helps having template code to copy over.
We got a special guest
coming over.
Right in time. Awkwardly, we changed our conference room setup, so it takes a couple seconds, but
Hey,
Hey,
everyone.
okay, it's David Mail
yep.
and everybody.
Nice to see you in person.
If anybody's
welcome.
watching and is unfamiliar with CS50, this is the professor of CS50 right here.
Yeah, nice to see
In
you.
the
In
flesh.
person, in the
Yeah.
flesh.
Doing
Thanks for
some
tuning in today.
doing some super
Yeah.
mathy stuff today. So
Yeah, we're going into some actual math.
Yeah,
a
I
little bit
see.
here.
I see a lot of Wikipedia over here.
yeah, there's
little bit.
some pretty decent math going on. We haven't even hit gradient descent, but we will shortly.
All right, some
And
big
that'll
words
hop in
today.
there. Yeah.
Nice to see you.
All the
everyone.
buzzwords.
See you online.
so yeah, thanks
Yep,
for
sounds
hopping
good.
in.
Thank you. Awesome. And so I think someone asked why log, why not root mean squared error? And so essentially because RMS is going to say, and actually there are other ways of manipulating this such that RMS would work, but with what we're actually trying to do is we're looking for across kind of a general categorization, how would our error be quantified? We use like a variant of log probability to do that. Root mean squared error would be based on basically the kind of linearity of the relationship, or that I could use a basis function to transform it into a linear basis, and from there get some sort of linear relationship. And so we're kind of just assuming that we don't have a linear relationship and there's no convenient way for us to get one. Now that sounds silly given that XOR, you can actually linearize that. You can get it to be linear. But in the general case where we're using a neural net, and let's say I have given, I'll put it in the context of what we have, an image, and I want to classify this image by what stream it came from, then it's actually really difficult for us to say what features are important and how they might be related. It's really tricky for me to say, okay, well here's a basis function that transforms all of our features such that every class is linearly separated. That's really difficult to do. And the more complex, the more features you have, and the more ways in which they're allowed to interact, the more difficult that becomes, usually. And because of that, we're kind of operating on the assumption that we can't use linear or strictly linear things in order to get this to work. Great question, and that's essentially why, it's the intuition at least. The math itself also explains that if you were to use a linear optimization function or error function or cost function here, that linear function would allow us to balloon in either direction. We might, for one, get stuck in like a local minimum on our loss function that like doesn't, not only never converges to a meaningful value, but if we were to hop out of that local minimum local minimum, then we might just like shoot upwards or shoot downwards or something poor. Poor behavior on our part. So what we're trying to do is have a function that has some global minimum that we can converge to by hopping to it somehow. Now, if people are like, why? What is this minimum you're talking about? What I mean is, if you were to plot this error function as a function of all possible predictions that could be made, or actually as a function of several of its parameters, then you should end up with this in the two-dimensional space. You'd end up with like a curve. It might have several local minima and then settle into a global one, or have a global one here and settle into local minima, things like that. And essentially what we're trying to do is hop around this curve and find that global minimum, because that means we have minimized our error based on the model that we have and the data that we have. And that's essential. That's essentially saying we understand our data. It's kind of what professors are looking for when they test you, presumably, is have you arrived at this kind of like global minimum, or are you stuck at some local minimum where when we test you, you'll fail. It's a rough kind of analogy, but it's the right idea. So we want this number, or the number that I've highlighted here, to be as small as possible. The absolute number is not necessarily meaningful. I think when I was showing Colton kind of what we were doing before the stream, it was like a 3. This time it's 0.7.
We got down to like 0.2 something.
Yeah, it's not super helpful to know what it is in absolute terms.
0.7 doesn't seem that good.
It's not super great, and intuitively it should start pretty high and then go down.
Yeah.
And if we change the way that we like initialize certain layers, so let's switch this to like a normal layer. Our number should change. It actually went up. So a normal distribution was much closer. We can kind of infer, not rigorously infer, but kind of intuitively infer from that. A normal distribution was closer to the actual distribution of the data. So it was closer to not the distribution of the data, the distribution of the ideal weights. And the kind of presumption is, and you can mathematically show this, that the ideal weights will minimize this error function. And that's kind of a circular argument, because the way that we define how we minimize our weights, or the way that we define how we get our weights, is by minimizing the error function. So it's two sides of the same coin. To argue that one is the cause of the other is a little weird, but it's really that we just want to minimize this number. And this, I guess if you look at how this works, it's a little bit tricky, but you're essentially multiplying something by, or you're multiplying a log by something, so you're raising prediction to the y.t power and then taking the log of that. And then over here, you've inverted everything. So we took this 1 actually kind of infers or assumes something about our categories. You can generalize this relatively easily, but for now, we're going to use just kind of this 1 as if we only have classes either 0 or 1, which we do. And then we have this 1 minus prediction, and this essentially says, okay, for the number of times, this is like the inversion. So if this was 1 hot encoded, now every wrong answer is now a 1, and every right answer is a 0. So there's a single 0 per each of these. And then in this NP log, anywhere that we have a prediction, we should have had as close to 1 as possible in the right place, but now we have a 0, presumably, and we're again doing the same thing. And so these are kind of just ways of measuring different like errors that could have been made in this, and then what we do is just add them together because they are linearly addable. And as Babbage says, this is a really sophisticated way to find a global minimum. Generally, you just do a first derivative, take second derivative, and you're done. And that's right for relatively simple functions. So in this case, I don't know if there's, that's called a closed form solution, essentially, that I can just do some math and find a solution for it. A lot of machine learning problems, that's not possible. The math behind it is too complex. We actually maybe don't even understand the math behind it. And because of that, we actually can't find a global minimum. There is no closed form, or I'm forgetting the term for this, but it's a mathematically derivable solution. I can't remember the name of it for the life of me, but it's literally only because I'm talking in front of people. If I was talking literally anywhere else, I could tell you off the top of my head. And so essentially what we're trying to kind of assume here is that in the general case where we're actually using a neural network, you actually don't have a closed form solution of any kind. We just kind of know that this sort of thing worked in kind of smaller cases like what we're doing right now, and it expands and generalizes well to more complex ones. So it would be very, very tricky and actually possibly mathematically intractable for us to try and find a global minimum using only math. Which is, I think, very wild. It's one of the cool things about ML and neural networks in general. It should strike you as very strange, especially if you're coming from like a high school or collegiate, linear algebra class, multivariable calculus class. Essentially, all of those problems are tractable, or they're non-tractable, and you just say, "Oh, it doesn't exist," and move on with your quiz or whatever. The problem is that a lot of those do not exist problems are really useful in the real world, and because of that, it's extremely important, and it's one of the motivations for ML to try and create machines that can solve those intractable problems that mathematically we don't understand, but they are
We're sort of
solvable.
emergently expecting them to figure it out.
More or less, yeah. Which is wild. It's one of those things that just blows my mind about this. Now, I did promise also that there is a backward pass, if you will. We have to communicate this new information that we have obtained about our error back to the hidden and output layers. We need to change their weights. So essentially, we need to adjust our machine's behavior based on what we now know. This is one of those things that tends to be really tricky for people, and I'm going to try and break it down into something that's a little bit more tractable, but if you're lost or confused, don't worry, it's difficult. It's something that you should probably like sit down and kind of like play through, but it's called backwards propagation or backprop. And essentially what it means is we need to teach our brain what we have learned. And so essentially what goes on, and I'm going to just kind of copy the code so that I can spend more time talking you through it, is I'm going to just copy all of this actually. This is from my template code. I promise I wrote most of it. And essentially what happens here is we have this two-step process going on. And what we're going to focus on first is the gradient part. So if you're familiar with mathematically what a derivative is, a gradient is kind of just an expansion of that concept into higher dimensions. So a gradient says, let's imagine that we have some surface, maybe like a bowl. It's just a particularly convenient surface. And I have plotted this in some way, or even in higher dimensions, they have ways of converging to a point. But in a bowl, it's pretty intuitively understandable. The center of the bowl is the convergence point. Now, if I take the gradient, and let's say I start it somewhere on the wall of the bowl, I want to dive down into the bowl. So if I take the gradient, what that tells me is it points that way, kind of up the edge of the bowl. It tells me the point of steepest ascent. So it says, hey, go that way. And that will take you to the maximum. So if we had an inverted bowl, it would take us to the top center. But if we have a normal bowl, we want to go down. And that's where the term gradient descent comes from. I have a gradient and it points upward, and I want to descend down that gradient. So if I take whatever my weights are, calculate their gradient based on some sort of parameters or inputs that I've given them, then I now know, okay, I don't necessarily know anything about the general shape of my surface or whatever I'm on. It could be like a valley or a tube or something. But I know that wherever I am, if I go that way, I will get closer to some version of the bottom. Now, I say some version because let's assume we have a big bowl and then like a little bowl that's connected. If I'm in the little bowl's wall, it might make more sense from wherever I calculate this that my gradient points me down to the middle of the little bowl, not the big one. And actually, you'll notice that it has to by continuity. So there's no way for me to just point at the dead center of the other bowl. Even if I could, I can't get there by continuity. I'd have to jump. And you might say, oh, well, then that's impossible. I literally cannot get to the global minimum. And that's where stochasticity and randomness are super useful. Having a reasonable variance, a reasonable kind of, we'll say, randomness in your data allows you to do what are called little hops. You can hop over that ridge between the big bowl and the little bowl, and you'll hop into the big bowl. And from there, you'll then descend to the global minimum. Now that is intuitively how that works. A lot of times they're not quite so easy for those, so to achieve those. So there's that, and it's definitely a difficult thing once you actually sit in the math, but I think that that's a good intuition for how it works. Bavik Knight says, yeah, what's with the upside down delta with a dot product? So that is actually it's called a nabla. It's an upside down delta, looks like a triangle, hashtag Illuminati. And essentially what it's doing is that says, what is our gradient? That is usually used as the symbol for the gradient function. And you can think of that as just the multidimensional derivative of your function. So essentially what we're doing here in our code is we want to calculate what the gradient is for our weights and for our bias. And we want to then descend that gradient. So we want our biases to be as small as possible. We also want our weights to be as, not necessarily minimum as possible. We want them to converge to something that is meaningfully useful. This gradient is calculated using the log probability as its kind of understanding. And then what we end up actually doing is multiplying by the error of what we have. So essentially what this does is this expands back out our error function and then uses it and its gradient to then calculate what our new descent should be. So these evaluate to numbers since we fill in all parameters, and then we subtract those numbers multiplied by some learning rate from the original parameters that we had. So that is called a backward pass. This all in total from here to here, possibly counting your error, is really the backwards propagation. So we're propagating all of the information we have now backwards through the neural network. This is why we stuck to a single layer neural network, was it makes this very easy. I don't have to do any weird syntactical tricks to get this to work. And even in here, there's a lot of math going on. I don't think it's super important to understand the exact math of why this works. I think the intuitive understanding is more general and more easily applicable. There are plenty of papers written on why this works for this kind of neural network. Something that we'll get into pretty much right after this is switching to a specific convolutional neural network. Each type of layer actually has its own way of doing backpropagation, or at least a different interpretation for what that means, because our gradients are calculated differently. So those sorts of things we'll have to go and deal with, and we'll go from there. So essentially what we now have is the kind of intuitive understanding of a single layer neural network. Intuitively, if we were to take this and loop it kind of just over and over again, we should be able to minimize that error. So for I in range, I don't know why, I was staring up at the screen and I was like, oh, this is cool. For I in range, we'll say 100, we'll say 10 to start. We should see this error go down. Now, whether or not that's true, we'll find out. Of course it's not defined, because I copied code from a previous version of this. You would think I would name my variables the same thing every time.
Probably not, no. Yeah,
but I just don't. Yeah. It's just not at all how I seem to operate. I get the concept right. I think it's the problem with knowing too many synonyms. It's you just don't.
That's why people say don't use single letter variable names too.
Exactly.
Because you run into the issue did I use J? Did I use K?
Every single time. Yeah. So I'm gonna just kind of debug my own code a little bit. I think that we're about right now. Nope.
Nintendo Doom 33 says CS50 and 3 blue 1 brown are getting me through university right now. Much love, you guys.
Nice.
Other people in the chat are saying 3 blue 1 brown's pretty good. I've never seen it. Are you familiar with it?
I have not. No.
People are saying
Sounds pretty cool.
or Nintendo was saying that it's got really good math visualization.
Oh, that is essential. I'm a visual learner myself, so that's why I kind of explain these things in like these weird hand versions of visualization. But oh my gosh, I'm losing my marbles.
And hello, Astley. Good to see you.
It's like I just never was consistent between like plural and singular for all of these. So give me a moment to kind of fix my like weird little bugs. This is incorrect. Of course it is. Oh, because I was gonna say I had a weird bug when I did this originally, and I was kind of like, meh, it'll work. And now I just need to debug kind of our like matrix dimensionality. Oh well.
Oh, that was what happened before we started.
Every time. I think that's about right. Cool. And then I just need hidden weight. This is hidden weights. There we go. Okay. Now everything, I think output weights, I think is, everyone's sitting there like, really, dude? You couldn't name your variables the same thing? It's like, yep, you got it. Cool, I think that gets it. Oh, and then I just need an eta. So eta is kind of a weird little symbol. We use it to decide how quickly we're going to try and learn. And essentially, if we try and learn too quickly, then we might descend and skip over things that are meaningful. Of course, they're not broadcastable. And that would not be great for us. In the kind of version of like, what was I gonna say? Where we like reduce eta such that we can kind of like hop down a gradient really, really slowly. If you have too small of an eta, then that's not super useful for us. So you kind of have to be like very careful with like how you actually control your learning, the learning rate, and that is usually what eta is. Now that learning rate simply refers to, we now have our gradient, how much of that, like we don't just descend by like an arbitrarily large amount every time, we want to descend by like a little bit in that direction, and the gradient is really just a direction at that point. And then I'm going to actually switch over to running the template code that I provided. I promise it's not particularly different. Now it's a little bit different. Cool. And then what we're going to do is go through this 100 times and print the error every 10. And you'll notice that our error doesn't go down a whole lot. Maybe we'll increase that to every like 100 or so. And then we'll put this at 1,000 and see if we can get this to show us something a little bit more useful. But essentially what's going on is we eventually converge to some actual error. You'll notice that our error should go down roughly. It starts at like 3.34, goes down a little bit, and then it kind of drops to like this 2.83 or so. And you'll notice that it actually like went even lower than that. That's not the global minimum of error, but it is kind of like we like bounced around a little bit. And the reason for that is if you imagine that we like got to the bottom of our bowl, but our learning rate was a little too high, then we might like ping across the bowl, right, and never actually hit the global minimum. And in this case, it's a trivial data set, so we hit our minimum pretty quickly and then kind of just like bounced around noise more or less. And because of that, we now have this error rate, and this is our neural net. Now this is not a very complex or interesting neural net. It's not super wild. There's all sorts of things about it that are a little bit weird. We don't do any sort of batching or like controlling for anything. We don't normalize. There's nothing interesting in terms of like complexity that we do here. We've just kind of implemented a very simple neural net to demonstrate a lot of the concepts. If you're interested in building more like complex ones from scratch, I would recommend using kind of like crazier, maybe like build a class so you can maintain interfaces and have better programming practices in general. I see a bunch of people are like, why aren't we using functional programming to do all the math? Python's fine, it's sufficient. We could switch to functional programming and also do math. The math will not get any easier, but you can make it look syntactically a little bit nicer.
What do they have you using the ML course here?
You're allowed to use pretty much anything you'd like. They basically suggest Python.
Oh, interesting.
Yeah.
Okay.
And so in our ML course, we actually just pretty much stick to Python. I would imagine that there are a couple people who use C++ just for like speed. I don't think anyone uses a functional language, not to my knowledge, but you could. The convenience with Python is there are so many libraries that are at a high level. So if we're like really rapidly debugging things and we're trying to just get it to work, then we're not going to be implementing all of this. We will just use a NumPy library, or sorry, a like TensorFlow library or a scikit-learn library, because the kind of reason for understanding this is so that you can improve your machine learning. But the reasoning behind like the actual kind of or like the need to actually build everything specifically, not so much. A lot of times those will work normally. Crazy Watermelon asks why it says convolution, and that's a great way to switch into our new version of this, or not a new version of this. My words are failing me entirely today. Too many presentations. We're on presentation number like 2 out of 3 today.
So today, what was your first one?
My first one was in my CS Big Data Systems class. I had to give a small presentation there, and like, I'm just wiped. There's just lots of talking today.
What's your next presentation?
And then my next one is on cybersecurity. So we'll be hacking some people. Although they've already been hacked, they don't know it.
You're gonna present some people with their passwords?
Pretty much. It'll be like, and is this your card? And they'll be like, that's my bank account. And you're like, no. Mostly kidding. That's all with their consent. So yeah, we have implemented kind of the like dense parts of a neural network. Now we're going to pivot into the why are we calling this convolutional? There's no images in this, and I'm glad you asked. That's exactly what we'll be doing. So we're going to kind of pivot entirely away from the like neurons and like dense like neural networks and where things are connected and backpropagation, and we're going to switch to, okay, you have a neural network architecture. We have these dense layers. I want to use this to classify images. And every pixel position of an image represents a feature. So let's say we have a really small image, like the MNIST dataset, MNIST. Now they're only 28 by 28 pixels, and they're not multi-dimensional like depth-wise. They're just single channels, so it's literally just 28 by 28.
Use individual pixels as features?
Yeah. And that's essentially because every pixel could be a feature. Now, if that sounds crazy, it is. In order to train a network on just raw features, which is what we actually did last time with our k-means stuff, but we weren't using a neural network, is wild. 28 by 28 is what? Like 784 or something?
Or 600 pixels?
Yeah, it's ridiculous.
Oh, yeah, it's closer to 700 something.
It's an absurd number, and we're not going to do that. That's crazy. So instead what we do is we reduce the dimensionality of our images while still retaining all their key features. So we're going to walk through some of the functions that do that. Now I'm going to delete all of the functions that do that from this file so that we are aware of how to build them. I'm going to keep load data so that we kind of like keep everything. Sorry, I also never got to using ReLU. It's another activation. This just takes, this basically just says it's rectified linear unit. And this says everything's linear unless you're less than 0, then just set you to 0. And so what this is saying is like given an image or a flattened image, then take anywhere that it's less than or equal to 0 and then set it equal to 0. I guess less than 0 would be sufficient, but we'll use less than or equal to for funsies. So we also have a way to load in data, and we're going to use that method. And essentially what that does, I don't know why I have that there, whatever. What we're going to use with this load data is we're going to load in our images, just the like, I think this is the Luma filter part of it. It essentially converts it to grayscale. So what we're going to do is I'm going to load in our images here. So I'm going to comment out our entire neural network. Oh, well, I was going to. There we go. Our neural network has now been commented out. And what we're going to do is play around with how do we look at these images. So let's load our data. I'm going to give it a data directory. I'm presumably going to give it a data directory. And essentially what we're going to do is take a look. Oh, I just used the wrong keyboard shortcut for that. We're going to give it a data directory. We're going to pull all these images. They're going to be NumPy arrays. We're going to do plot.figure, plot.imshow, and plot.show. And I just want to see what does like the first image look like. Now, if you were here last time, oh, of course that doesn't. Why does that not work? Oh, okay. there we go. If you were here last time, you'll notice that this essentially, of course, it's not defined. All my packages are gone. I don't know why I said it like that.
Digivolts, hi from Peru. Hello, Digivolts. Thanks for joining us all the
hey.
way from Peru. That's awesome.
I'm probably going to need another couple of things. So from pill, import image, I think. I think that's all of them. We'll find out shortly if that's not true. Yeah, that worked. Cool. And
Oh, wow.
that is not what I wanted. What?
Interesting.
Did I highlight that? Nope.
It's it like took out all the white and now it's yellow.
Yeah.
And then like
What the heck? Let's go take a look at what this is doing. So load data says image.open of f, convert L, maybe LA? Does that work? That might throw an error dimensionality-wise. Yeah, that's bad dimensions. Meh, that should be right. Nope.
they look pretty great.
We look weird. Yep. I mean, great is a way to do that. Andres is like, yeah, that's not black and white. I agree. Why is that not black and white? That should be black and white. Maybe we could convert it into gray and just see what happens. L should be the luma parameter. Also, I'm wilding because I tested this earlier. Let's think about what I'm doing. Oh, sorry. I'm silly. I forgot to map it to the gray color map. That's gray.
Nice. What color did you see it as earlier? Because I know you see
Yeah,
colors
so I
slightly
see colors a
differently.
little whack. I saw it mostly as like a green-orange kind of deal.
Okay.
Yeah, so
Okay.
pretty close. I think it was yellow,
Yeah.
right?
Yeah, that was
Not too
yeah,
bad.
that's roughly right.
And now it's black and white. There we go. So essentially the values that we got are not like actually gray scale. You'll notice that they can be mapped to gray, but the default is not in the right like dimensionality, or not the right range for grayscale, so we got that abomination. Yeah, so here's our grayscale image, and this is what the original image looks like. Now, what's going to be really useful to us is to say, okay, that's what the original looks like. Let's try and pull some interesting features out of this original image. And
So now is it just a matrix instead of RGB? Is it just a matrix of floats from 0 to 1?
0 to 1, or I think this one's probably like 0 to 255. The color mapping just kind of like rescales it so that it can be mapped to gray. That's the essential piece that I forgot. So what we might want to do is we might want to take our first image. I'm just going to alias that so I don't forget. And now we can just do this. And we want to take that image and pull out interesting parts to that image, interesting features, if you will. Now, it's not necessarily intuitive to us which features are meaningfully interesting, but generally there are some features that are interesting enough. So let's say that I design some filter. We'll call it like our line filter. And this is going to be a NumPy array that is going to consist of a couple of rows that are like 0 dot, 0 dot, and so on. And I'm going to just kind of copy and paste these. So we have now 4 of them. Let's make 8. And because our images are pretty big. So we have 8 of these zeros. And then I'm going to put like a 1. And then I'm going to put 8 more zeros. And this is kind of one row of our filter. And then I'm going to just kind of copy and paste this a couple of times to get a roughly square filter, but not entirely. So this is a 17 length filter. Currently, I think that's 8. So here's this. And now it's a square filter, I believe. Cool. So that was a lot of manipulation for a very simple looking array. You'll notice that it, I believe, is square. You know, we can double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Crap. And I think we just need one more. Oh, actually, I can just paste. Cool. All right, I think that that's right. Let's print out our just line filter dot shape. I don't think we do still show the image. Sorry. I'm a mess. There we go. And this is now 18 by 17. Oh, I just miscounted. Well, not a shocker. Okay, so now if we print this out, this is a 17 by 17 image, I guess like pixel set. We can actually even we can plot it, which is kind of cool. I think that's kind of cool. I don't know. And essentially what we will then see is just a block of just a single white line, right? And essentially what this does is it says, okay, we have a single just bar down the middle. It's a square filter, but it's just a single bar. And this is looking for white bars. Now, if I wanted the opposite of that, I could just do this, do that. And now we have the opposite, a single black bar.
How is it? Why is it 0 being white if the 0 normally is black?
So now I've just flipped them. So now anywhere there was a 0 is now a 1, and anywhere there's a 1 is now a 0. So black is still 0, and white is still 1. So highest intensity is still white, lowest intensity is still black. We flipped what our filter actually looked like by doing this 1 minus. So now the filter that we had.
Oh, I thought you did 1 plus.
Yep. Nope. Sorry. So now our highest intensity things are black. Or sorry, our high intensity things are still white, but they're the majority of the filter, and then everything is below. Andrej says typically you average the values. So typically is a very strong way of phrasing that in this case. There's not necessarily a whole lot of typical in this. There are ways that are typically taught in terms of like how to get you familiar with this. I just am going to cover the the pooling part of this after. So in this case, we're using a filter to look for particular features, not necessarily to combine things. So we're not really reducing the dimensionality of our data, but we are saying, hey, if something has this characteristic, then cause this behavior, otherwise cause this behavior. And hopefully that makes sense. There are actually 2 parts to what we're about to talk through. The first part is convolution, so how do we put a filter and push it over the image entirely? And then the next part is how do we pool them? Oh, I see. So Andres clarified, this is me talking to Bobek. Sorry, I didn't read everything. I just kind of read parts of it. I got you. But yeah, what I said is still true. We're still going to go through and split them apart into convolution and then pooling. I see. So Andrej was actually talking to how to grayscale a pixel. You can average all the values. That is one way to do it. There are many ways of doing it. I just use an inbuilt method because I didn't actually want to do that. Sorry for misunderstanding. Cool. So we now have this kind of enormous, glorious filter. And what we want to do is convolve the image. Now, convolution in signals processing has a slightly different meaning and usage. That generally means and I'll just kind of show you because it's easier to demonstrate via picture. Convolution of signals. And with an image, this becomes fairly easy to see. An illustrative one is probably this. And so basically, if we convolve 2 signals, that kind of, I don't know what color it is, but the one that I've now traced with my mouse, that's the convolution. The thing being convolved, the thing being convolved with is here, it's this box, and then this triangle is the convolution, or the operator, the filter that it is being convolved. And wow, that was the weirdest phrasing I could have used. Essentially, this is a depiction of a signals processing convolution, and it's very similar in concept. But what we're actually ending up doing is creating more of a cross-variance matrix and kind of moving from there. But I wouldn't worry too much about that. Convolution is just kind of convention. It's the name of the term, and we're going to create a function that allows us to do that. So let's go ahead and build our define convolution. Our convolution function. And this is going to take some image and some filter. And I think filter is a safe word or a specific word in Python, so I'm not going to use it.
Yeah, it's a function.
Osley says, I love to see the new quote of the day on Nick's laptop. Yep, my quote of the day is all over the place. If I open up a new terminal window, you get a new quote of the day. Well, sorry. They're always weird quotes. They're from Kause, so I take no responsibility for what comes up on those. All right, so we essentially now want to say, okay, we want to convolve something, and this filter is going to require us to kind of understand, given where the filter currently is, we're going to multiply it across everything that exists in that space in the original image. We're going to take the sum of all of those, and that is going to be our result of the convolution. Now, if that sounds kind of similar to multiplying across by all the weights in something, like in our neural net, then you're absolutely right. That's essentially the analogous thing that we're doing here. Our weight is essentially our filter, and the image is the data. And so we're multiplying each representative part. The way that that gets done is a little less simple than it used to be in just a plain neural net. And we do usually add a bias term, which is why you also have backpropagation for the convolutional layers in your neural net. We're going to not do that here. We're going to just kind of motivate what a convolution can look like and how different convolutions kind of change our image. But be aware that the actual convolutional layers that are used have a bias component, which we're not going to use or demonstrate. And when they're part of a neural net, they are also part of the backpropagation step that goes on. But I don't think that it's educationally useful to implement all of that. I also would not be able to do it off the top of my head. I would need to kind of like see which ones are kind of around. And see just kind of like what the math is behind it, or I'd have to write it down and kind of derive for a while. So we're going to just go through simple convolutions. So now what we're going to do is call this image height, image width. Sorry, this also assumes we're using a single image, which is again not necessarily convention, or wouldn't be. And we're also assuming single channel. So this extends fairly easily to multi-channel images, but we're not going to do that for now. And then I want the filter's height and width, which I'm going to just call h and w, and that's fill.shape. There's no error handling here. It's funny to me that everyone freaks out in C code if you don't error handle things, but in Python, no one cares. And that shouldn't be the case. You should care a lot about how this is error handled. There could be all sorts of bad inputs to this, but we're going to ignore them for the sake of brevity and clarity of what we're reading. And what I want to do is I want to know what like the output shape is. So I'm going to do like output is actually just np zeros. I think it's shape. Dang it. And the shape of this isn't terribly crazy to kind of go through, but what we're going to assume is that it's really just like image height minus height, and then plus 1 by image width minus width plus 1. And the reason for that is like once we get to the end, there are other ways of handling this, but I'm going to just kind of like ignore it. So this will reduce our dimensionality kind of by accident by a little bit, but not really. So we're gonna say that this isn't a dimension reducing step because it's not, but it does kind of bring out some of the features. So in that sense, it's kind of like a feature reduction almost. Like there are noise features that don't really matter to us or just noise, and we're kind of trying to eliminate that. And so this is the shape of our output, and it's just a bunch of zeros for now. And what we want to eventually do is return that output. And then what we're going to do from there is we're going to iterate over our image. Now this is by no means the most efficient way to do this, but it is illustrative of the point. So I'm going to use ij, I is our row, j is our column. For j, I looked at it, thought to myself was like I, and then I said j. I meant I. For I in range of, and again, this is going to be this kind of like parameter here. So we're iterating through all of the rows of our output. And then we're going to, all the rows of our output for j in the number of columns in our output, and that's going to be this parameter. And all I want to do every time I get here is I want to say, okay, output at I comma j is going to be equivalent to np.sum of np.multiply of, and in this case what happens is we say, okay, what does our filter look like here and what does our image look like here? So this is our image from everything from wherever I is to I plus h, which is our filter's dimensionality, and then wherever j is to our j plus w. And now we have kind of like a block of our image that we are now trying to multiply our filter across and then sum up. And I think multiply finishes here, and we can just multiply that by the filter. Now normally you would also add this like bias term here. We're not going to do that in this case, again, just to illustrate the point. And that should be our convolution, unless I made a mistake somewhere. So let's go ahead, and instead of im showing our line filter, let's im show the convolution of our image and line filter. And let's hope that no errors occur. We're still printing line filter.shape. I'll stop doing that. And we can then go over here. Now, this is a much blurrier form of the image that we had previously. Hopefully you can tell that we don't actually look like that. If you can't, look to the bottom, I think, right of your screen, and you'll see what we actually look like, in full color, too. So this is a very blurry form of what's going on. You're like, what happened? What things have been strengthened? What things have been weakened? This is wild. But essentially what we're doing here is we're saying, okay, we want to like kind of look for things that have this linear part, this linear kind of like space in between them, and those things should be emphasized. Those are real features for us. Anything else we're going to kind of just ignore. Now, if I modify this such that I'm not doing the 1 minus part, and it's just the filter as it was, we'll get rid of this, and we'll rerun it. Now this you'll notice is a very different image. It's blurry still, but in a very different way.
It's like a vertical blur, kind of.
Yeah, in this case, we vertically blurred again, but this time we were looking at anywhere that we had kind of like our individual white space has now, or like kind of a bar of white, has now been emphasized, if you will. Now, usually you use a couple of, well, maybe not usually, but I have seen used a couple of convolutional filters that are looking for varying kinds of feature. I could look for curvature, for example, and we can try and build like a small version of that. So I'm going to just kind of like go through and get rid of all these ones.
One Track System says, first time watching y'all will not be the last. Much love for sharing your understanding.
Awesome, thank you. Yeah, we really appreciate that.
Thanks so much.
And what we're going to kind of do is look at this like, and I'll do like a length or size 2 curvature sort of deal, where we're looking to like approximate what like a kind of curve might look like. And the reasoning for this is essentially like what might a curve, kind of a very tight hairpin curve look like here. And sorry, this is very sloppy.
Like the most terrible way to draw a curve too.
Yeah, possibly. I suck at drawing curves in general.
And then drawing them within matrix.
Yeah, if you think this is very easy, please go ahead and try. And if you succeed, please send us the code. This is a huge mess. I thought it would be great to do this live. I was like, oh, in my
it's
head,
like
this
a
would be
less
perfect.
than sign.
Yeah, it's really kind of a sharp hairpin kind of curve here. It's also not symmetric, in case that wasn't bothering you already. It goes the wrong way. So yeah, in case you are like really OCD about that, that's terrible. And you'll notice that what this did is, again, you get this kind of weird blur effect, but it's essentially convolved as it goes, looking for wherever any sort of curvature like this occurs. If you have that curvature, then it gets emphasized, and if you don't, it gets zeroed out. Now, you can make that emphasis effect stronger in colored images by multiplying by like a factor of 10. And you can do other things to get that to happen. In our case, it shouldn't change anything as far as I'm aware, because it's grayscale, so it just gets refactored out. But you could do things like that. We'll do a slightly simpler filter, because this one's fairly large and it's hard for me to manipulate in real time. But let's say we did like a 0, and then we did like a 1, a 2, a 3, a 2, a 1, and then a 0. And essentially what this is saying is anytime you have something that goes from like left to right and grows in intensity and then diminishes quickly, those sorts of things will now get emphasized in the right kind of contexts. And what this helps us kind of understand is when we apply it to our image, assuming I added an extra thing there. This doesn't necessarily do anything wild to our image, and that should hopefully be a little bit intuitive in that these values are very close to each other, so when they get rescaled, nothing really changes. But if I emphasize them a little bit more, using this kind of approximation, then what I can do is I can do this, and I'm keeping them roughly square so that we don't distort our image too much, but you can use any size of filter as is hopefully observable here. And as we go, then in this case, we see slight differences. I don't know if they're as visible on the big screen as they are on mine. You see actually a little bit more distortion. It's hard to see up there. It's pretty easy to see on my computer. Yeah, you can see that your like shoulder's a little bit blurrier. My shoulders get a little bit blurred because anytime you have like this delta in intensity, you're going to see sorts of changes as they go. Whereas like my hair to there, you can still see the outlines pretty clear.
Yeah.
And so like you basically end up being able to see, you can account for different kinds of change. And so that's really useful to a machine is there are certain filters that are like canonically known to have certain properties that tell us, hey, this is super useful, this is really not. I look for straight lines, I look for curves, I look for hard transitions like a delta. And basically if you understand your like matrix algebra, you can implement a lot of like any linear function as a matrix. So you can implement most forms of like derivative as a matrix, for example. And that's a really useful property. Bob Knight says it's hard to see. Sorry, it's not necessarily super wide. I could make the filter bigger for it to be a little bit easier to see, but that's you can implement it yourself and kind of look on your own computer. And so that's what we can do with filtering. So we now have a way of convolving our image with itself and doing all sorts of things. And I'm going to kind of keep a filter. I'm going to keep a vertical bar filter around. So we're going to use a 5-piece vertical bar. we'll say, actually, we'll just do like, whoa, that's not a number. What the
Like
heck?
a sigma?
I think it was a Q.
Uh,
Yep. Not always the best at typing. I'm never the best at typing. That's okay. It's not necessarily my only needed skill. All right, so this is a 5 by 5, I think, if I counted right, and this will be kind of our filter to go to from there. I'm also going to still use the like 1 minus part of this, not 1 equals. There we go. So the second part of this that we promised was pooling. And pooling basically says, hey, I have this set of pixels. I now need to understand, what's the most important attribute of these pixels, of this group of pixels. And so a lot of times the common way of doing this is doing max pooling. We're going to implement a general pooling function that can take max, min, median, whatever. And what we're going to do is, again, an image. We have some pool size. We're going to just initialize that to like a 4 by 4. And then we have the pool function. Oops. Oh, that's not right. Which we're going to just set to numpy max. So by default, this will implement max pooling, which is pretty common, but we could swap out that pool function for like min or median or mean, and it would do the same. And so what this is going to do is we're going to say, okay, kind of similar to the like setup up here. So I'm actually going to just like copy paste this, and then instead of fill shape, we have pool size, no shape. And now we've kind of parallelized what convolution is to pooling. And again, we have our output, so I'm going to copy that back over, because now all of our parameters are the same, except in this case, what I'm actually going to do is a little bit more math. And I'm going to divide that by the height. And then I'm going to, oh, sorry, I should do this. There's a lot of parentheses that go into this. OK. So that should be what our height is. So we're essentially just assuming that the pool does not overlap, is what we're now implementing. It's very, very similar, but it's off by a little bit. And then I'm going to just replace these with W's. Gotta love naming convention. OK, cool. So now what we're doing is our output is of roughly the same size, except we're dividing out the factor of the size of the pool. And the reason that we do that is because now, every time we try to pool a segment, we don't include anything from that segment in the next pool. Now, this is not the most general implementation of this. The most general way is to include something called a stride. And actually, even convolutions can also have this stride parameter. We just didn't include it for kind of brevity. But for general, the most general way to do this would be to include a stride parameter, and that stride says how many over do I skip when I'm moving the pool. So maybe some parts of the pools overlap, not all of it. Maybe the whole thing does, or most of it. So if the whole pool overlaps, you're just pooling the same thing over and over again. Not useful. But your stride should be at least 1. And then after that, you can kind of move over. They should intuitively be integers. But I can then, if it's 1, then that's what our convolution was. This is implicitly a stride of 1. I'm going to always go over by 1 pixel, do my calculation again, go over by another pixel, and do it again. And then when I reset, I'm only going down by 1 pixel. So you can see how that might be very computationally intensive. Convolving tends to be, or convolutions tend to be pretty computationally intense. Pooling tends to be a little bit less because you're trying to reduce the dimensionality of your data. And that's exactly what this does. So again, we're going to iterate over. Actually, it's not quite the same iteration. So we're going to iterate over for I in range. Except this time, it's a range from 0 to whatever your output dimension is, or your output number. So we're going to keep it kind of as this image h minus h plus 1, but we're going to skip by h. And hopefully that makes sense. It's essentially just a reformat of the way that we put this, except this time we're skipping by h's instead of dividing that out, because otherwise I have to do a little bit more integer math to get this to work. And this just, I think, is a little bit simpler to understand. But if you don't like that, go ahead and do it yourself, and you can change it. Cool. And we do the same thing for going across. Sorry. And so now that we have this done, our output is actually going to be written like this. Our output is the integer result of, well, I guess I could just do this. I divided by h, and then, j divided by w. And now, since our j's will be indices that correspond to the image that we're pooling over, we want to convert those indices back into the output indices, and that's what this is. And then all we have to do is apply our pool fx. And you'll notice that pool fx should return, oh my gosh, some actual number. If it doesn't, then this will just fault all over the place, and nothing will, or it won't really technically fault, but it'll have errors. And what we're then going to do is do this over wherever I is to I plus H, and then wherever J is to J plus W. And hopefully that makes sense. Again, you would have a bias term and things like that. But we're going to kind of just ignore that for now. And the reason I bring it up is because when we were talking about all this like backprop in a neural network, that's where it would come into play in this layer. And then we're going to just return output. Cool. And I think that that is our pooling, basically our pool. And so if we do pooling on our image, and we don't need a line filter anymore, but we can say, well, yeah, let's give it no other parameters and just see what happens. So we're doing a max pooling, nothing broke, and we'll notice everything got pixelated a little bit.
Things very jaggy, yeah.
Yeah, and you'll notice too that things that are lighter are now more important. They're more significant. So essentially, to make that a little bit more dramatic, let's do pool size, and let's make this a 32 by 32 pool. And our image isn't super large, so that should be pretty pronounced. And you'll notice that when we pool over this, we've basically just said, okay, there's a white blob here, there's a white blob here, and this black part is still there, but there was literally nothing white in it. If there had been like even a single white pixel here, it would have been the maximum and it would have become representative of its block. So essentially what this says, this pixel here says, is there was literally a pure white pixel and it was somewhere within this entire block. It has now been pooled here. So this image, this pooled image, I'm going to kind of like pull out from that function, and I'm going to say our pooled 1 equals that. And we're going to put pooled 1 back in here so that we can see. And I'm going to actually change the function that it uses. Also, that's wrong. There we go. We're also going to add that we don't really want like max isn't necessarily representative of what the image should look like, right? Like that doesn't really tell us a whole lot. So again, people would use multiple of these sometimes use multiple of these in order to gain many features. Now what this says is, okay, take the minimum one. And our lowest intensity values are black images. They're the darkest color. And so what this tells you is like, hey, this segment actually had a lot of lightness in it, such that even when we were taking the minimum, we still ended up with something that wasn't pure black. Same thing here. These pixels were all white. The entire thing was white. Same thing here, except for this little segment. And then there's like a little variation here. So now it might make sense for us to say, well, we don't want it to be so dramatic. Like that's kind of a lot.
Bhavik just said we calculated the reverse of the enhance.
Yeah, exactly. We have just kind of, you know how in like NCIS, they kind of like are like enhance and it gets clearer? We're doing the exact opposite of that. We're dehancing it. We're just like, boom, it's way less clear. And I'm going to actually print out the image's original shape so that we can see how this reduces dimensionality. Intuitively, you should be able to kind of think, oh, well, we're only going over so many parts of it. It reduces it by roughly the scale. So whatever the pool, oh my gosh, whatever the pool size is, it's kind of like if we divide each corresponding term by the pool size, we end up with what the actual scale is. Now I've reduced the pool size, and now we get a little bit more understanding of like our individual features and things, which is cool. And I'm going to swap this out one more time for mean, which is kind of the mathematical average. Now, our dimensionality reduction is the same. We still reduce it by the exact same amount, but we now have a little bit clearer of an approximation of people, which is maybe meaningful. So it might be meaningful for our neural net to learn, oh, if I see something that has this kind of dark here and this white here, then that's like a person, and this is also a person, but that is a board or something. That's a very weird way of phrasing that, but it's the right kind of concept. So now what we might do from there is we have this single pool, and I'm going to just start putting titles on these because we're going to plot a bunch of them. Yeah, I'm not going to dynamically do that. So now let's say that we want to we pool like the mean first, and we're going to use a pretty small pool at first. We just want to get it to pool a little bit. And then from there, we're actually going to convolve it a little bit. It's not worth the convolved 1 equals convolution.
Is mean the most useful function that we're looking to use too?
Not necessarily. A lot of people actually use max as their most useful function, but also you can use multiple of these. So you can have multiple layers that pull out different features as we go. I like to use mean in this case because I'm just trying to reduce dimensionality, and then I'm going to convolve it, and then I'm going to reduce dimensionality again, but it'll be a little bit different meaning. Gotcha. So in this case, we're just kind of assuming that I got an image that was just way too big. I can't process these fast enough. I'm going to use mean to kind of retain in general what was there, but I want to reduce the dimensionality by about a factor of 16, so 4 by 4.
Right.
And so once I do that, I can say, okay, let's do a convolution where our image is now pooled 1, and our filter is our line filter up here. So we do like this line filter. There's no other parameters we need. And then here, I'm going to just plot that now. Oh my gosh, what was that? A complete catastrophe. And this will be convolved 1. Oops, did I put a space? Nope. And this will now also be convolved, if I could spell. There we go. And now when we run this, I'll stop displaying those shapes. People understand, I think. And so here's our pooled 1. So we only pooled by a little bit, so we just kind of like pixelated a little. It's not huge, it's not crazy. We just kind of reduced our dimensionality a little bit, but it was meaningful to us. We scaled it down by 16. So it's clear as like a human, we didn't lose a whole lot of information, but we made it a lot faster for us.
Right.
Now from here, then we do this convolution, and you'll notice that this convolution is a lot more dramatic than the one we had before.
Yeah.
And the reasoning for that is we're now doing it over fewer
like
things.
double vision.
Exactly. And it's kind of like if we were to pass like a line over it and then say, hey, like what things do you see on either side of this line, right? And it's literally what happened here is we just kind of like blocked out part of like the middle and then just kind of like scanned across. And so you get this like weird stuttering pattern almost.
Yeah, like the weird, like where the left side of my head meets the blackboard looks a bit weird.
Yeah.
Too.
Right around here, I think your ear got chopped off.
Yeah.
Is essentially what happened. And the kind of reasoning for that is that we had this vertical bar, and that's what we were checking. So we've now done that, but I've done this convolution. I now know what kind of features are really important from that. I want to kind of repeat this. I want to pool again, but this time I'm going to pool using just the max of the features maybe, and I'm going to call this pooling 2. And I want our filter to be a lot larger, maybe like a factor of, that would be like 4 times larger. And so, and I'm going to use np.max here. And I know that's the default, but I'm going to use it anyway just to be explicit. So again, here's our pooled 1. Here's our convolved 1. Now when we do pooled 2, oh, sorry, I did that on the image itself. I was like, well, and we're back to roughly the same thing. Confusing. Yeah, so here's our convolved 1.
Literally the same thing.
Yeah, it was literally the identical thing. I was like, that's whack. So here you go. This is better. Pooled 1, convolved 1, and now our, that's not what I wanted. That is not at all what I wanted. Okay, this is convolved 1. Oh, I'm literally, yeah, sorry, I'm literally showing you pooled 1. I was like, that can't be right. Let me just double check myself before I embarrass myself for a 4th time. Yeah, this is, okay, that should be right. Cool.
Nice.
I was like, what is going on?
Looks pretty close to what the other one was. Yeah.
Yeah, and it looks very similar to as if we had just pooled the first one like this as it was.
With using max,
right?
yeah.
So if we wanted to like double check that, we could replace this with max, and we would see that that's roughly true. Let's increase the size of our filter here, though, and from that we should be able to kind of like convey what's going on. But we're again going to use mean. And we're going to kind of try out what this does. And so you'll notice that we're even more distorted this time. So things got carried over. And then when we convolved it, things got even more distorted.
Wow, yeah,
so that one's a lot more blurry. But you'll notice that we retain this kind of like gradient around each of our like descents across things.
Yeah.
And that's usually pretty useful, is like, where is there a gradient, where is there not? You can also do the opposite, where you want to really sharply define, kind of like increase your contrast, if you will. And when we do this, now this looks meaningless.
It's just
right?
nonsense.
It's just nonsensical.
I mean, if you know what it is, you can still tell. But.
You do, yeah. You could kind of like still intuit what's going on, but it's roughly meaningless. Now, it's meaningless to us-ish. Like we kind of know there's like white up here, there was a person here, there was a person here, and there's a blackboard behind them. But let's imagine that this was in color still. Then having like a blue blob here, for us in human terms, that represents me wearing a blue shirt that day.
Yeah.
And a kind of like darker color pattern here, whereas other ones might be a little bit lighter, represents you wearing your glasses. And so this might actually be a really useful feature map for a machine who's trying to classify which stream we're in. Because this feature map will look very different from this stream as opposed to the next stream.
True.
And in order to kind of illustrate that point, I'm going to grab the image from the opposite end of the streams, so we should be somewhat different looking.
Okay.
And we'll compare the two, probably not side by side, but we'll compare them. And so what we're going to do is just copy this entire segment. So this is terrible code design. If you're looking for what not to do in a code review, this is it. And we're going to, okay, well, I should have put more spaces there because now I can't tell where it starts.
I think down a little bit, right there.
Yeah, perfect. And we're going to just redefine image as images -1. So this is from the complete opposite stream. So we're going to go through these again. This is the original one that we're looking at. And we kind of see the progression as it gets pooled. Here's pooled 2. Now, if we go to the next image, completely different, right? It's a very different image.
Yeah, you and I are on different sides too.
We've also switched sides, and that's really important. You're also not wearing your glasses in this one.
Yeah.
And so now as this gets pooled, again, the convolution just kind of like, it looks like it just kind of blurred everything. But here, this pool 2, if you can kind of remember what the previous pool 2 looks like, is completely different.
Yeah.
And that is kind
There's
of
still the light
part
corner
here.
in the top right, though, that white box.
That white box is still there. And so this, to a computer, is a lot easier for it to process because we've reduced its size by a substantial amounts, by non-trivial amounts, and we can now flatten this. And so that's kind of our last layer to throw in here and describe how it works. And flatten's fairly easy. Flatten is just saying, hey, given an image, let's get the height and width, and that's going to be image.shape. And then we're going to just return np.reshape of image to be of the size height times width, comma. And essentially what this just does is it says, okay, we can flatten this image out to be just an array of numbers, but you'll notice that array of numbers is what we can throw through a neural net.
Right.
And now we have the ability to kind of combine this all together to be a convolutional neural network. These 3 layers, kind of this convolutions, pooling, a lot of times they're used in pairs. So like I'll convolve the image, I'll pool it, I'll convolve it again, and then I'll pool it. And once I've kind of like broken those apart and like gotten my important features out of it, then I'm going to flatten the result, pass that into the dense layers of my neural network, and at the end it'll spit out a class. And so the next time we're on this stream, you'll see us build these without building the actual independent like pieces on our own. We'll just use an API, but you now should have a pretty solid understanding of where these things came from. They have extra features and kind of knobs that we can adjust, but this is the essence of what's going on in each of those layers. And essentially what we're trying to motivate is this sucks to implement on your own, and there's a lot of places for reusability and optimization, and that's where a library like TensorFlow is extremely useful, is we can then just access each of these things. The reason that I think it's helpful to build an intuition on these things is, let's say that you have 2 pooling layers and 2 convolutional layers, and they're intertwined, and your classifier is just not getting it. It's just not, it has one class of images that it keeps mistaking for another class, and you're not sure why it's doing that. You're really annoyed, and you're like, what the heck is going on? And you remember, oh, well, you know, there's all sorts of kind of problems with if I'm convolving by the right set of filters. Maybe my filter set only includes 2 filters, and they look for vertical bars and horizontal bars, but the distinguishing characteristic between class 3 and class 4 is not vertical versus horizontal, it's convex versus concave curvature. Well, vertical and horizontal, convex and concave have roughly the same amount. I mean, if they're like parts of a circle, convex versus concave have like the same amount of vertical and horizontal, so you can't distinguish them. But if you were to add a concave and a convex filter to your filter set, you are now capable of explaining, 1, why your classifier now works, and 2, how everything actually interacts, and you can kind of intuitively understand where that came from. That would be part of the convolutional step. If we wanted to say, hey, my machine learning network is taking super long to train, but I'm pretty sure that it's just using a bunch of redundant or irrelevant features, or maybe it has way too much variance and it's mispredicting all over the place when it tries to generalize, then what you might say is, oh, maybe I can just reduce the dimensionality, try to boil it down to these key features, and from there I can then reduce training time for 1, because my dimensionality is reduced, my feature dimensionality is reduced, but also I now have only the meaningful features contained, so I'm not going to generalize poorly. So when I then get a new piece of data, I can generalize to that data a little bit more intuitively. The noise isn't going to freak me out. That's what that kind of like, kind of boiling it down to its mean helps reduce like high variance noise, and then reducing feature dimensionality from there is also useful. SAR-LCS says, so basically these transformations are to reduce dimensionality of input images for classification. Not purely just that, kind of for all the reasons we've just enumerated, they do a lot of other things. They're very powerful transformations, and convolutions allow you to pick out which features are important. So convolutions themselves don't actually reduce the dimensionality at all, or at least not meaningfully. They essentially just say, hey, these features have been emphasized, and here's what an image with those features emphasized looks like. And so you might then create a composite image that has several of these kind of like convolved layers in it. And that composite says, oh, okay, well, in this image, these features are really important. In this image, these features are really important. And it's really useful for your machine to then be able to distinguish between those. But then we want to be able to pool those features back together to allow us to figure out what features are actually important. And that's where your dimensionality reduction actually comes in. I think what Andres says is it essentially a polarizing operation. I think kind of by intuition, yeah, that's roughly, so polarizing kind of means like we're pushing them separate in two directions. I think the general form of that is about right. It's kind of like, how do we distinguish between different images, and it's kind of like how do we pull out or emphasize certain features so that we can then compare those features across images. And I think that that's what you meant, which is perfectly right. So yeah, these ideas they definitely take a couple of kind of passes in order to forward and backward, if you will, to understand. And neural networks are by no means simple. They're not even fully mathematically understood, but it's definitely I think here you have an intuition for why they work, what they do, at least at this is even still a fairly high level. If you wanted to really dig into it, there's a bunch of white papers, there's a bunch of Khan Academy tutorials. You can go and look through the math. I would recommend a decent like probability or statistical understanding and a decent understanding of like linear algebra. A lot of these things base themselves in like probability theory, like log likelihood theory, and linear algebra theory. So how many matrices do you know how to manipulate and things like that. But I don't think that should scare anyone away, essentially.
Yeah, I think it was pretty cool. I mean, a lot of it definitely flew over my head.
Yeah, no worries.
It was cool
Takes
at
a
the
long
very
time.
end. It was cool at the very end to sort of see what you were doing and why it was important. Yeah, I think I'm going to spend some time doing a little bit of research on the math for all this stuff. But no, thanks so much for doing this part 2. And I guess next week, part 3, we'll go in. What would you say would be the outline for next week?
So I think next week we can look forward to building we'll set the goal of like a style transfer at the least, and kind of just building that. And then our eventual goal is to build these sharp adversarial images. I think style transfer gives us kind of the understanding of how you can actually use a convolutional neural network beyond just a classifier, because they are still kind of used that way. Convolutional neural networks are really well suited for classification tasks, but we're trying to push towards the direction of how do we use them to generate new images.
And how would you define style transfer? What does that mean?
So style transfer is going to say, hey, given let's say a piece of art and a image that I have taken, like a photograph, can I get the photograph to look in the style of the art that we have?
So make us like a Van Gogh painting,
exactly.
essentially.
And I think that that's kind of our next step.
Okay, yeah, that would be super cool. Well, thanks everybody for tuning in. So we'll do that again. We'll do it next week.
Yeah, we'll be here next week.
Sounds good. Tune in tomorrow for just me. We're going to do part 2 of our chat codes, everything in the stream, which turned out quite well.
It was pretty good.
It was pretty entertaining.
Awesome.
We did a chaos run, and then we did a goal where we basically made a square, like an ASCII square.
Oh, nice.
So that was we had a lot of trolls in the chat. I'm not gonna lie.
Sure. Yeah.
All in good humor, of course. It was fun.
Of course.
And it was fun seeing how people like got around people like obviously trolling the script.
Right.
Like some people would be like, okay, amend this line to actually do this instead, and it's like okay. But yeah, no, it was great. And so thanks to everybody who's going to tune in, who tuned in today and who might tune in tomorrow. If you're watching this on YouTube, you can tune in to twitch.tv/CS50TV to watch CS50 live. Or if you're on Facebook, same thing.
Yep.
And tomorrow we're going to be able to do libraries. I think I'm going to add the ability for people to do like a pip install, like request a pip install.
Sweet.
I might have to vet them just to make sure they're not like custom libraries.
A custom library.
That just like this is completely malicious. So probably like well-known libraries. But if people want to get kind of fancy and do stuff like that, we'll do a couple of hours of that tomorrow. And then on Friday, if you haven't already, definitely submit at cs50.loi/code review. David is going to do a code review on Friday, and also if you're in the well, let me see if I can get a link to our Discord actually. We're trying to potentially take live suggestions via our Discord. So let me just see if I can get the CS50 Discord link here. So if you are watching this and you go, and you can also just kind of get access to this by doing a Google search for CS50 Discord. Let me make sure I'm in the right thing here. It's this one. You can go to the CS50 Discord. That's an invite. It's a public invite, so you can join the Discord channel. Definitely do that. There's a bunch of subthreads. Post in the #live code review channel on the Discord when we're actually going live or in advance, and I'll curate it and we'll potentially show it live on stream. So it's a fun time. It's a fun time.
That's awesome.
And then next week we'll do a whole bunch of more fun stuff. So thanks again so much.
Yeah, thank you.
This is cool. Overwhelming, but at least for me, but I actually am inspired by it to dig in, I think, a little bit more in my math and get a little bit more comfortable.
Yeah, no, it's the whole goal.
Yeah. For some reason, the thing is freaking out. I can't do.
Oh, your
Alt
keyboard
tab.
shortcuts are.
Yeah. What is going on? Okay. Yeah, it is completely freaking out. But
Complete
anyway,
mess.
thanks everybody so much. This was CS50 Live Neural Nets Part 2. Next week we'll do Neural Nets Part 3 with Nick.
Yep.
In the meantime, stay safe, and I will catch all of you tomorrow. Bye bye.